All right, so hi everybody, welcome back. What we're doing today in this video is wrapping up the chapter 10 lecture on rotational motion. So by the end of the video, we'll be completely done with chapter 10. And where we left off last time is we started to talk about how you can combine rotation and translation. So you can look at an object that is both rotating and translating and know how to analyze that type of motion. So a classic example of this is rolling. An object that is rolling along the floor is translating and rotating at the same time. So let's get into this. If an object is rolling without slipping, what we mean by without slipping, is that the underside of the body and the ground do not slide past each other. Okay, so in other words, there's some point on the rolling body that's in contact with the ground at any time. And that point is at rest relative to the ground. It's not sliding across the floor. So let's take a look at an animation so we can get a sense of this. So what you're going to see in this animation is this red wheel rolling across the ground. And I want you to pay special attention to this blue point, which is on the outer edge of the wheel. So you see the path of that blue point being traced out as the wheel rolls along the ground. And so take a look at what happens when that blue point actually touches the ground. So just before it touches the ground, that blue point is moving straight down. And then just after, it's moving straight up, which means for that tiny moment in time when it's touching the ground, it's at rest. Okay, so it's at rest relative to the ground. And that means there's static friction between the wheel and the ground in order to prevent it from slipping. Static friction, not kinetic. Okay? And again, to give you another sense of this, to give you a sense of the idea that the point of contact with your rolling object and the ground are not sliding past each other, they're at rest relative to each other, even though the wheel is rolling, let's take a look at this photograph of a rolling bicycle wheel. Okay? So what you see in this photograph is parts of it look blurry because there's a lot of motion, but other parts of it don't look blurry at all. So if we look at the very top of the wheel here, as it's rolling, that part looks very blurry because that part is moving very fast. But if you look at the bottom, there's less blurring in the photograph, meaning there's less motion. And in fact, if you look at the very bottom of the wheel that's in contact with the ground, that's going to be, again, momentarily at rest relative to the ground. So that's the idea of rolling without slipping. Okay, so let's take a closer look at rolling without slipping. Here, I'm going to put my water bottle on the table, and then I'm just going to give it a little push so it starts to roll. So what you just saw there was the water bottle rolling without slipping, meaning the underside of my water bottle and the table were at rest relative to each other. They're not sliding past one another. Another way of saying this is there's traction between the water bottle and the table. Now, ideally, this is what would be happening with your car's tires as you're driving down the road. You want your tires to be gripping the road. You don't want them to be sliding along the road because that would mean you're skidding, or another way that could happen is if you're just sort of spinning your wheels and not even moving at all. Okay, so this is an example of rolling with slipping. And what's happening now is, of course, the underside of the bottle and the table are moving relative to each other, and there's kinetic friction between them. Okay? So that's the difference between rolling without slipping like this and rolling with slipping like this. Okay, so now hopefully you have an idea of what rolling without slipping looks like. So the next thing to do is develop some equations that describe this type of rolling motion. So in this derivation, we're going to look at a wheel that's rolling along the ground. Its radius is r. And we're just going to look at a tiny little bit of rotation that it undergoes. Let's say it rotates through an angle d theta. So if it rolls and rotates through an angle d theta, the center of mass of the wheel, shown here, is going to move some distance to the right, okay? So that's what we mean. It's rotated through some angle, and at the same time, the center of mass has moved some distance. Now, the distance that the center of mass has moved is actually equal to an arc length along the wheel. So this is what we'll call dxcm, the distance that our center of mass has moved from the initial position to the final position. Now, that's equal to a length of arc along the wheel, along the edge of the wheel in particular, which would be given by r times d theta. That's how we specify an arc length. You take the radius and then multiply by the angle, which here would be d theta. You can imagine that if the outer rim of the wheel were covered in paint, you would leave a little line of paint this long along the ground, and that would be equal to the arc length on the edge of the wheel. Okay, so dxcm, the distance the center of mass moved, is r, the radius of the wheel, times d theta, that little angle that it rotated through. So with that, we can start to talk about the speed of the center of mass. How fast is the center of mass moving? Well, that would just be the distance you move, which is dxcm here, divided by the time it takes to do that. And again, the distance, we can replace that with r times d theta, and that's divided by dt. So you should recognize this piece, d theta over dt. What's that equal to? That's what we call omega. In other words, that's the angular speed of the rotation. So there's a relationship between the speed of the translation, vcm here, and the speed of rotation, omega, if you're rolling without slipping. And in the same way, we could talk about the acceleration of the center of mass. So maybe as the wheel moves from here to here, it's accelerating in some way. Well, that would be the derivative of vcm with respect to time, right? That would be the derivative of velocity with respect to time. So we'd be taking the derivative then of the previous result, which would be r times omega. But of course, r is a constant. You can pull that out. And then we're just taking the derivative of omega. So what's the derivative of omega? The angular velocity, that's called alpha, the angular acceleration. So there's also a relationship between the acceleration of the translation as you move from one point to another and of the rotation alpha. And again, it's just a factor of r, a factor of the radius to go from one to the other. So to summarize, we've just derived what are called the no-slip conditions. Okay? If an object is going to be rolling without slipping, then there's a relationship between the linear speed of the center of mass and the angular speed of the rotation about the center of mass. Okay? And this is the relationship. We have vcm, magnitude, so we're talking about a speed here, is equal to r times omega. Also, we're talking about a magnitude here. And this only works if the angles are given in radians, because earlier in our derivation, we said we had an arc length, which is equal to r times d theta. That part only works if the angles are given in radians. So we have to carry that assumption over into this. Okay, also, the linear acceleration of the center of mass is related to the angular acceleration of the rotation about the center of mass. And that's given by this relationship here. We have ACM, the magnitude, is equal to r times alpha, where we're taking the magnitude of that. And the angles are given in radians. So I just want to make one thing clear about this. These relationships only involve magnitudes. Okay, so if we want to get the directions of these vectors correct, they're VCM, omega, ACM, and alpha, these different vectors. If we want to get the directions correct, it'll depend on the context of the problem. Okay, so all we know is that the magnitudes are related this way. And those are the no-slip conditions. Okay, so let's do an example where we have an object that's rolling without slipping. and we can apply these no-slip conditions to the object. So here we have a uniform disk of radius r, initially at rest, but it's subjected to a constant force that acts at the center of mass. Okay, so there's where the force is being applied, and that force we'll call F. Okay, as a result of applying that force, it begins to roll without slipping along this horizontal surface shown here. What is the linear acceleration of the center of mass of the disk? So what we're going to do here is find the answer symbolically in terms of F and m, which is the mass of the disk. So in order to do this, something that's going to come into play is the moment of inertia of a solid cylinder, a solid disk, which is given by I equals 1/2 mr squared. That's the moment of inertia of a solid cylinder that's rotating around its center of mass. Okay, so let's work this one out. Okay, so in order to do this problem, we're going to need to understand all the different forces that are acting on the disk. So we'll draw a free body diagram of the disk. So we're looking at the disk from the side. So there it is. The center of mass is right in the middle. And there's a force F being applied right at the center of mass. So let's draw that force. But what other forces are present here? Well, we should immediately think gravity. And one fact about gravity that I'm just going to give to you here, we're going to see this in more detail later, but gravity acts at the center of mass of an object. Okay, and we'll see more on this in chapter 12. But for now, let's just take it as a fact that gravity acts right at the center of mass. So if I have that force vector W for the weight pointing down, I'm going to put that right at the center of mass. Okay, we also have a normal force because this disk is being supported by a surface which pushes up on it. And that force will act at the point of contact with the surface, so down at the underside of the wheel. And then we're also going to have another force. That's going to be static friction. We need static friction in order for this wheel to roll without slipping. Because, look, if all we had were these three forces, as you pulled along the center of mass, the wheel wouldn't even roll at all. It would just sort of glide along the surface without even rolling. You need a static friction force acting at the underside of the wheel, right at the point of contact, going against that tendency to just slide along the surface, so going to the left in order to make it roll. Okay? So let's now have a coordinate system that we can refer to. Let's say x is going to be going to the right, y is going to be going straight up, and then z is going to be coming out of the page like this. So that's the coordinate system that we'll use. And so let's start writing down some equations. Remember from the last lecture that for the translational motion, we have Newton's second law. The net external force in the x direction is the mass of our object times the acceleration of the center of mass in the x direction. Okay. Now, in this case, we have two forces that act in the x direction. We have the force F going to the right, and then we have static friction going to the left. So that will pick up a negative sign. And that should equal m times ACM, the acceleration of the center of mass in the x direction. And we can take this further, but for now, let's just leave it as is and call that equation 1. We'll come back to it later. Okay. Another thing we can write to describe how this thing is moving is a torque equation, or the rotational version of Newton's second law. The net external torque in the z direction is equal to I. That would be the moment of inertia of this wheel times alpha z. Okay, so let's take a really careful look at this. We have 4 different forces, right? But some of them might not even produce a torque, okay? So this wheel is going to rotate about the center of mass. So that's going to be our axis of rotation also. And right away, we see that there are 2 forces, W and F, that act at the axis of rotation, which means there's no torque. I mean, think about this. If you were trying to open a door by pushing on the hinges, of course, that would have no effect. That's kind of the situation here. If you apply a force right at the axis of rotation, there's no torque. Also, the normal force N, the line of action of that force, if we kind of follow it this way, goes right through the axis of rotation. So this also doesn't produce any torque. So the only force here that's producing any torque is the static friction. And again, this goes back to what I said earlier. If you didn't have any static friction, the wheel wouldn't even start rotating in the first place. So it's only static friction that's creating any kind of torque here. Now, in general, we know that a torque is given by R cross F. So, for the static friction force, R is the radius of the wheel. The force is Fs. And we'll have to take the sine of the angle between, let me draw the radial vector R right here. The angle between that radial vector, which goes from the axis of rotation to the point down here where the force is applied, that's at 90 degrees to the static friction force. We also have to worry about the direction here. So we can use the right-hand rule for this. The R vector is pointing straight down. So take your right hand, put your fingers so they're pointing straight down. Then curl them in the direction of the force, which is to the left. And now your thumb should be pointing into the page, which is the negative z direction. So that picks up a negative sign. Okay. On the other side, I have the moment of inertia, which is 1/2 times m times r squared, and then we have alpha z. So we can simplify this a bit by dividing through by r, and also by -1. So the negative sign goes to this side. I just have Fs left on the left-hand side. And then I have minus 1/2 times m times r times alpha z on the right side. Okay. So let's leave that equation as is and just say it's equation number 2. We'll come back to it if we need it. Okay, there's one more equation that I need to account for. And this is what we call the no-slip condition. Okay, if this wheel is really rolling without slipping, then the linear acceleration of the center of mass is going to be equal to the angular acceleration times r. But again, those are just magnitudes. So when it comes to the situation we have here, our object is accelerating in the positive x direction. So the acceleration of the center of mass in the x direction is positive. But if we think about the angular acceleration, alpha z, that's actually negative because here, what kind of rotation is happening? This type, this clockwise sort of rotation. And that corresponds to a negative value of alpha. The point is, these two have opposite signs. And so when we plug those into the no-slip condition, we have ACM x equals minus alpha z times r. So those two just have opposite signs. All right then. So I can plug that into, let's call this equation number 3. Let's plug result number 3 into result number 2. Okay, so remember number 2 says Fs is equal to minus 1/2 m times r. And then alpha z, I can write that as minus ACM x divided by r. So the two negative signs cancel. Now we have a positive sign out front. 1/2 m ACM x, like that. Okay, because the radius cancels, yeah. Okay, now plug that result into the first equation, which is up here. We have the force that you're pulling with, F, minus the static friction, which we just said is 1/2 m times ACM x. That's equal to m times ACM x. Okay, so we just plugged this in right here for the static friction. Okay, so we're almost done. The force that you're pulling with is equal to 3/2 times m times ACM x, just by adding this to the other side. And therefore, ACM, the acceleration of the center of mass of this disk, is going to be 2 times F divided by 3 times m. And that would be the answer symbolically. That's how fast it's accelerating. Now, let's compare this to something else, okay? So compare this to just dragging an object across the floor such that it's not rotating. So compare it to, let's say, a no rolling condition, no rolling case. Let's say you just have a box. You're just dragging it across the floor this way with force F. Well, in that case, if we do the net force in the x direction is equal to m times acceleration in the x direction, it's a lot more simple now. We just have that one force equals m times ax, and ax gives us F over m. So for the case where it is rolling, okay, it accelerates slower than the no rolling case. Okay, it's harder to get it to accelerate when it's both rotating and translating at the same time. Okay, so next, let's talk about the kinetic energy of a rolling object. So a rolling object has two types of kinetic energy that we have to account for. We have to account for the translation and the rotation. So it has kinetic energy due to the fact that the center of mass is moving from one place to another, and due to the fact that it's rotating about its own center of mass. So the total kinetic energy of a rolling object would be the rotational part, k rotation, plus the translational part, k translation. Now we have formulas for each one of these. Remember, for rotation we have 1/2 I omega squared, and for translation we have 1/2 mv squared, but in particular we're talking about the speed of the center of mass here, okay? Now, if we're dealing with an object that's not slipping as it rolls along a surface, then you can use the no-slip condition where VCM, the speed that the center of mass is moving with, is equal to omega, that would be the angular speed over here, times r. So you can relate them with the no-slip condition. So let's do an example. Let's say we have a bowling ball with a mass of 5.75 kilograms that's rolling without slipping down a lane at a speed of 3.75 meters per second. Let's find the total kinetic energy of that rolling ball. So let's work this out. Okay, so we're dealing with a rolling object, so the total kinetic energy is equal to the rotational kinetic energy plus the translational kinetic energy. And for rotation, we have 1/2 I omega squared. For translation, we have 1/2 m speed of the center of mass, that's VCM squared. Okay, so a couple things. The moment of inertia of a solid sphere is given by 2/5 mr squared. So this is a solid sphere that rotates about its center of mass. And that would be the case, of course, if we have a bowling ball. Okay. Another thing we can say is that the no-slip condition tells us that VCM is equal to omega times r, or we can just as well say omega is equal to VCM divided by r. So if we make these substitutions, K total then becomes 1/2. I, the moment of inertia, is 2/5 times mr squared. And then omega, we can replace that with VCM over r. And that gets squared in the equation. And then we have 1/2 times the mass times VCM squared. Okay, so the first term can be simplified quite a bit. Cancel out the factors of 2. Also the factors of r squared. So we're just left with VCM squared and a factor of 1/5 and m out front. So 1/5 times m times VCM squared is added to 1/2 times m times VCM squared. So we have 1/5 plus 1/2 m times VCM squared. We can combine those two fractions to just give us 7/10 m times VCM squared. Okay, so let's put in the numbers. We have 7/10. The mass of the ball is 5.75 kilograms. The speed of the center of mass is 3.75 meters per second, and we square that. And this gives us 56.6. If we think about the units, we have kilograms, and then we have meters squared divided by seconds squared, which is a joule. So this is 56.6 joules of kinetic energy. So notice how it has more kinetic energy because of the fact that it's also rotating than it would have if it were just translating, okay? Because we have to account for both types. We have to add them together. And instead of just 1/2 mv squared, we get this factor of 7/10 out front. Now, if it was a different shape, like a cylinder, you'd get a different factor out front. It's not always going to be 7/10. So what you should do is just work it out from the beginning like this. Okay, so the next example I want us to take a look at is an object rolling down an inclined plane. So what I want us to do here is consider the general problem of an object with mass m and radius r that rolls without slipping down an inclined plane. Now, we don't really have to specify what the object is. It's just something that is round and symmetric that can actually roll. And for example, it could be a hollow cylinder, a solid cylinder, a hollowed out sphere, or a solid sphere, or any number of things. But again, it's just some kind of round symmetric object. And when we're dealing with a case like that, the moment of inertia is given by this general form. So we have I, the moment of inertia, is equal to some number beta times mr squared. So beta is just some kind of number, some dimensionless constant. So if we're dealing with a hollow cylinder, beta would be equal to 1. So we would have I is equal to mr squared. If we had a hollow sphere, beta would be equal to 2/3. So I would be equal to 2/3 mr squared, and so on. So I'm just giving you in this table different objects with different values of beta. So what we're going to show is that the object's linear acceleration, so the acceleration of the center of mass as it rolls down the ramp, is given by g sine theta over 1 plus beta. So we're going to derive this result two different ways. First, we're going to use Newton's laws of motion, and then we're going to use conservation of energy. I'm actually going to show you the demo with different objects rolling down a ramp, and we'll see how they accelerate at different rates. And then finally, we'll talk about what this result means, how we can get an intuition for it. So let's get started on that. Okay, so we'll start by drawing a free body diagram of the rolling object. So this is what it will look like. We have the ramp. Let's draw the surface of the ramp right there. Make some angle with respect to the horizontal, theta, which we'll show right here. And now let's draw the object itself. It's something round and symmetric, whatever it happens to be. This is what it will look like from the side. And the center of mass is right there in the middle of the object. So we have to think about all the different forces acting on this object. Well, one of them would be gravity, the force of Earth's gravity, where the weight is pointing straight down. There's also a normal force because it's being supported by a surface. So if this is the point of contact between the rolling object and the ramp, the normal force will act right at that point, and it should be pointing out of the ramp, perpendicular to the surface of the ramp. Now we also have a static friction force, which is going to point up the ramp. Remember, we need static friction if the object is going to roll without slipping, because if that were not there, then the object wouldn't even roll in the first place. It would just slide down the ramp without spinning. So you need a static friction force going up the ramp to account for the fact that it's actually rotating. So next, we're going to set up a coordinate system where the x-axis is going down the ramp, the y-axis is going out of the ramp perpendicular to it. This is typically what we do when we're dealing with inclined planes. And then the z-axis is going to be coming out of the page towards us. So that's what we'll use to keep track of directions. Next, now that we've established the coordinates, we can break this force vector w into components. So we'll have wy right here and wx right there. So the components along the x and y axes. There's a right angle between x and y. And the angle theta, same angle that the ramp has, is right there between wy and the vector w. So let's do a little bit of trigonometry to break this into components. Remember, sine theta is the opposite side over the hypotenuse in a right triangle. In the triangle we just constructed, the opposite side is wx. And the hypotenuse would be the magnitude of the vector w. So wx should be the magnitude of the vector w times sine of theta. And remember, the weight is given by m times g, so we have mg sine theta. Okay, so next, we're going to apply Newton's laws. We're going to do it both for translation, in which case we have the net external force acting on this object is equal to its mass times the acceleration of the center of mass of the object. And we also have the net torque. The net external torque acting on the object is I That's the moment of inertia times alpha, angular acceleration. Okay, so for the force equation, for the normal version of Newton's second law, F equals ma, we're going to write the net force in the x direction is equal to m times ax. So we're going to focus our attention on the x direction for now. And what that gives us is, well, we have wx, the x component of the weight going down the ramp. So that carries a positive sign. But we have the static friction force going up the ramp, which carries a negative sign according to the coordinates we just drew. And that should equal, again, m times ax. Okay, so when it comes to wx, we worked out that's mg sine theta. So we have mg sine theta minus fs, the static friction, equals m times ax. Let's call this equation number 1. Okay, next, we can say the net torque in the z direction is equal to I times alpha z. What does that give us? Well, there's no torque being produced by the weight because that acts right at the center of mass. That's right on the axis of rotation. The normal force also doesn't produce any torque because, just like before, if you follow the line of action of the normal force, it goes right through the axis of rotation, goes right through the center of mass. So the only thing that is causing a torque is the static friction force. That's the only thing that induces a torque about the object's center of mass. So remember, torque is given by R cross F. So the magnitude would be the magnitude of R, which should just be the radius of the wheel. So I'll use a capital R for the radius of the object. The force would be the static friction force. Remember, that's what's causing the torque here. And then the angle between those two is 90 degrees. So this force acts at a 90-degree angle. If we think about the sign, it's going to be negative according to the right-hand rule. So again, let's just kind of sketch this out real quick. X, that marks the axis of rotation. So R goes from the axis to where the force is being applied. The static friction force is being applied this way up the ramp. So here's what you do. Point the fingers of your right hand in the direction of R and curl them in the direction of the force going up the ramp. And now your thumb should be pointing into the page in the minus z direction. So that's where the negative sign there came from. Okay, on the other side of the equation, we have I, the moment of inertia. Well, remember, that's beta times mr squared, where beta can vary depending on the type of object we have. And that multiplies alpha z. So let's simplify this a bit. The static friction force, the magnitude of that, is equal to beta times m times r times alpha z, and don't let me forget the negative sign that's in front of that. So that's going to be the second equation. Okay, the next thing we'll do is apply the no-slip condition. This object is rolling without slipping, meaning the acceleration of the center of mass, the magnitude of that, is equal to the angular acceleration times the radius of the object. Okay, now in this case, the object is accelerating down the ramp. So, in other words, its acceleration in the x direction is something positive. On the other hand, if we look at the angular acceleration, so the wheel is going to start rotating this way, clockwise. If you curl the fingers of your right hand in that direction, you're going to see that your thumb is pointing into the page. So our angular acceleration is into the page, which is the negative z direction. Okay? So the point is to say these have opposite signs. So AX is going to be equal to minus alpha z times r. Let's say that's our third equation. So if we plug the result of that third equation into the second, in other words, static friction is minus beta times mr times alpha z, which is minus ax over r, according to the third equation. Cancel out the negative signs as well as the factors of r to say that Fs is equal to beta times m times ax. Okay, now what we're going to do is plug that result into the first equation, and that's going to give us, we have mg sine of theta minus Fs, which is beta m times ax. That should equal m times ax. So we're about to solve for ax. Notice how the mass drops out. It doesn't matter what that is. And we have g sine theta on this side. We have minus beta times ax, but if we add that to both sides, we put it on the other side of the equation. We have a common factor of ax. We have a factor of 1 from this term here. We're going to pick up a factor of beta from this term right here. So when I go ahead and solve for ax, the acceleration, the linear acceleration down the ramp, we get g sine theta over 1 plus beta. That's the result we were trying to prove. That's how you do it using Newton's laws. Okay, so now let's see how we can solve this problem using conservation of mechanical energy. So let's draw the system. We have a ramp. We have an object that's rolling on the ramp. So let's say in the initial state, when the object is up here, that it's at rest. So we start the object off from rest, but then after some time, it's going to roll down the ramp and end up down here. Let's say this is the final state. And it's going to have some velocity. The center of mass, in other words, is going to have some velocity, indicating that we're translating. Also, it's going to be spinning or rotating this way at some rate omega. Okay, now let's indicate the angle of the ramp here, theta. And let's indicate the distance down the ramp that the object has moved. Let's call that x. So one thing we'll need to do is keep track of the height of this object, and we'll do that using the y-axis here. So the initial height is y initial, the final height is y final, and we're free to set the 0 point wherever we like when it comes to the y-axis. So why don't we just say y final is equal to 0. Then if we do a little trigonometry, we'll see that we have a right triangle where x is the hypotenuse, this is the angle theta, and then y initial is that vertical side. So sine of theta is opposite over hypotenuse. The opposite side here is y initial. The hypotenuse is x, so y initial is x sine theta. So let's put that on the diagram. Y initial is x sine theta. Next thing we can do is make a table of energies. So our system has some energy in the initial state and in the final state, and we can break it down into the different types of energy that we need to keep track of. In particular, we have rotational kinetic energy, we have translational kinetic energy, and then we also have gravitational potential energy. In the initial state, We're not even moving, so there's no rotational or translational kinetic energy. Just put zeros there. Then we have mg y initial for the gravitational potential energy. In the final state, we end up with no gravitational potential energy. That would be 0, just because we go to y final is equal to 0. Then for rotation, the kinetic energy is given by 1/2 I omega squared, and the translational kinetic energy is given by 1/2 m VCM squared. Okay. So the next thing we do is we set the initial total mechanical energy equal to the final. Again, all the different kinetic and potential energies, we just add the columns, essentially. So this is E initial, this is E final. So for E initial, I have mg y initial, that's it. For E final, I have 1/2 I omega squared plus 1/2 m VCM squared. So remember that y initial is equal to x sine theta. On the other side, we have 1/2 times I, and I is equal to beta times mr squared. That's the moment of inertia. Then for omega, remember if the object is not slipping, let's say the no slip condition, VCM equals omega times r. That's the no slip condition. So if we apply that here, we can replace omega with VCM divided by r, and then we'll have to square that. And then I have 1/2 times m times VCM squared. Okay, so first thing to note is we can divide out the mass. That goes away. On the left side, now we just have g times x sine theta. On this side of the equation, we have a factor of 1/2. Also notice the factors of r squared cancel here and here. We're just left with VCM squared here. I also have a common factor of VCM squared, so I can pull that out as well. And then in my first term, I'm just left with beta. And in my second term, that just multiplies 1, so beta plus 1. Okay. Now, VCM, what is that equal to? VCM is going to be, well, let's say VCM squared first. Multiply through by 2, so we have 2g times x times sine theta. Divide through by 1 plus beta. And then, of course, we'll square root that to get VCM. Okay, so that's the speed of the center of mass. That's how fast it's translating. But what we want is the acceleration. Okay, so that's going to take one extra step. What I want to do here is rewrite the expression for VCM in a slightly different way. So we have the square root of 2 times g times sine of theta over 1 plus beta. And then we have the square root of x, basically. Okay, but all of this stuff in front of the square root of x is one big constant. So instead of writing all of that stuff over and over again, I'm just going to call it c. Okay, so that's just a constant, which I'll refer to as c. So a more compact way to write this is VCM is equal to that constant c times the square root of x, which we can write as x to the 1/2 power. Okay? Okay, so let's take that. And starting up here, we'll say that ACM is the derivative of VCM with respect to time. In other words, acceleration is the derivative of velocity with respect to time. But we just said that VCM, the thing we're taking the derivative of, is c times x to the 1/2 power. So how do we take the derivative of this? Got to be really careful here. We're taking the derivative with respect to time, not x. Okay, and x is the variable that appears in this equation. So in order to do this right, we have to use what's called the chain rule. That means we first take the derivative with respect to x, which gives us 1/2 times c times x to the minus 1/2. So in other words, we take the power of 1/2 out to the front, we reduce it by 1, so now the power is minus 1/2. But we're not done yet. Now we have to take the derivative of x with respect to time. That's how you do the chain rule to properly evaluate that derivative. Okay, well, we have dx dt in that expression, don't we? But dx dt is just the velocity, right? The derivative of position with respect to time is just the velocity of the center of mass, which we said is equal to c times x to the 1/2 power, okay? So for ACM, here's what we have. I have 1/2 times c times x to the minus 1/2. And then remember, for dx dt, I'm subbing in c times x to the 1/2 from the line of work we just did above. So now I have a half. I have c squared. And what happens if I multiply x to the 1/2 times x to the minus 1/2? Well, I just get 1. Okay. So remember that constant c that we defined earlier? That was the square root of 2g sine theta over 1 plus beta. We're squaring that guy. So we just get rid of the square root, cancel out the factor of 2, and then we have g sine theta over 1 plus beta. You get the same answer. Okay, that's the acceleration of this rolling object as it rolls down the ramp. Same result. Okay, so let's take a closer look at the result we derived and try to understand what it means intuitively. So we have ACM is equal to g sine theta over 1 plus beta. And that number beta is a constant. It appears in the moment of inertia formula. And different shapes are going to have different values of beta. But notice what the formula is telling us. If beta is larger, if we increase beta, since it's in the denominator, then the acceleration is going to decrease. Okay, and if beta gets smaller, then the acceleration is going to increase. So in other words, for objects with smaller values of beta, they accelerate faster down the ramp. They're actually going to roll faster down the ramp. So if we look at the table where the hollow cylinder has a value of 1, hollow sphere 2/3, solid cylinder 1/2, and then a solid sphere 2/5, this is in decreasing order of beta. As we go down this table, the objects should be rolling faster. In other words, this is telling us a hollow cylinder is slower than a hollow sphere, which is slower than a solid cylinder, which is slower than a solid sphere when it comes to rolling down a ramp, okay? Now, what does beta actually mean? What is the meaning behind this number? Well, beta is a measure of how the mass of an object is distributed. If an object's mass is concentrated closer to the center, then beta has a smaller value. If the mass is spread out as far from the center as possible, then beta has a bigger value. So in the case of a hollow cylinder, the mass is very spread out from the center. In the case of a solid sphere, it's very concentrated towards the center. That's what beta is telling you. And again, objects with smaller values of beta, with mass more concentrated towards the center, are going to roll faster down the ramp, okay? Okay, So let's take these ideas that we've developed about how objects roll down a ramp and put them to the test. So according to the equation we derived, certain objects will roll faster down a ramp than others, and it depends on the shape of the object. So let's take a look at a head-to-head race between two different objects. We have here a hollowed out sphere. This is a tennis ball, it's basically air on the inside. This is a solid sphere, and according to the equation we derived, we expect the solid sphere will win the race. It will roll down the ramp faster. So let's see if that's actually the case. So we're going to start them both at the top of the ramp at rest, and then I'll remove the starting block and they'll start rolling. Okay, so it looks like the solid sphere won the race. It went down the ramp faster. Let's do another head-to-head race between, here I have a hollow cylinder, just a ring, and here I have a solid cylinder. So let's see which one of these rolls down the ramp faster. And we put them in a head-to-head race. So let's go. Okay, very clear winner there. The solid cylinder rolls down the ramp much faster. So let's do a couple more head-to-head races. Let's say we'll take the solid cylinder and the solid sphere and match them up and see which one gets to the bottom faster. Okay, so solid sphere versus solid cylinder, what do we have? Okay, looks like the sphere won that race. Again, that's exactly what's predicted by our equations. And I don't know, how about we do one more? Let's say, let's take a hollow cylinder and a very small solid sphere and see which one is going to win the race. So place your bets, and here we go. Okay. So the sphere rolls down the ramp much, much faster. So again, this is exactly what we predicted using the equations of rotational motion, and it does in fact work out this way. So it's always good to test these ideas out experimentally. Okay, so I'm going to give you an example for you to try out. We have a ball placed at the top of a ramp, which is angled at 25 degrees relative to the horizontal and is 1.9 meters long. It rolls without slipping all the way to the bottom. What is the speed of the ball's center of mass when it gets to the bottom of the ramp in meters per second? So solve this problem by using conservation of mechanical energy. I kind of showed you how to do that already just symbolically, so here you're going to do it and actually calculate a value for V. So in order to do this, you're going to need to know the moment of inertia of a solid sphere rotating about its center of mass. That's going to be given by I is equal to 2/5 mr squared. Okay, so pause the video, give this a shot, see if you can get it, and then we'll go through it together. Okay, so let's solve this problem using conservation of mechanical energy. So the setup is pretty similar to what we did earlier, but let's go through it again. We have a ramp, some angle theta, and the distance down the ramp is d. Okay, we want to keep track of the height of the object that's rolling down the ramp. So we'll do that using a y-axis. And y initial is the height at the top of the ramp. Y final is the height at the bottom. Let's just set the 0 point to be the height at the bottom of the ramp, so then y final is equal to 0. And that would mean the initial height up here is d sine theta. Okay? So let's make a table of energies, just like we did before. So the object starts up here, ends down here in the initial state. The object is at rest. In the final state, it's rolling. It has some translational motion, so the center of mass is moving at some speed. It's also rotating, so there's some angular speed omega. And in the table of energies, we're going to have the initial state in one column, the final state in another. And then the types of energy are kinetic energy for rotation, for translation, and also the potential energy due to gravity. So just like before in the initial state, because we're starting from rest, both types of kinetic energy are zero. Also, the initial potential energy is mgy initial, but the final potential energy would be zero once we hit the bottom of the ramp. Then for the final rotational, we have 1/2 I omega squared. For the final translational kinetic energy, we have 1/2 mvcm squared. So initial column equals final column when we add up all the energies. Initial is mgy initial, that's the only term there. That equals 1/2 I omega squared plus 1/2 mvcm squared, just like that. Okay, well, a couple substitutions. Again, y initial is d sine theta. The moment of inertia I is equal to 2/5 mr squared, solid sphere. It's the shape we're dealing with. And then, of course, the no slip condition tells us that VCM is equal to omega times r. So we're going to use that as well. We're going to make these three substitutions into the equation above to give us mg d sine theta, that's the substitution for y initial, equals 1/2 times 2/5 mr squared, that's the moment of inertia I. And then for omega, we can replace that with VCM over r, and we have to square that. And then we have plus 1/2 mvcm squared. We'll just leave that alone. So mass drops out. Then we have g times d sine theta equaling, I also can cancel out the r squared factor here and here. And basically each term is multiplying VCM squared. The first term, I pick up a factor of 1/5. The second term, I pick up a factor of 1/2. So overall, that is 7 over 10. So we have GD sine theta equals VCM squared times 7 over 10. Now, VCM squared is then going to be 10 over 7 GD sine theta. Of course, we want to square root that. So we have 10 over 7. G is 9.8 meters per second squared. D is the distance down the ramp, 1.9 meters. And then theta is the angle of the ramp, 25 degrees. The answer is 3.35 meters per second, which is 3.4 meters per second when we round it to 2 sig figs. So that's what the answer would be for a sphere. If you had a different shape, the answer would come out differently. So keep that in mind. You have to actually follow all these steps to see how it works out. We've seen a whole bunch of examples of an object that is rolling without slipping. So now let's take a look at an object that is rolling while slipping. What does this look like? So we have a wheel with the radius r is equal to 12 centimeters. It is initially rotating clockwise at 15 revolutions per second and not translating. So the wheel is just spinning in place. It's not translating in any particular direction. But then the wheel is lowered onto a horizontal surface where the coefficient of kinetic friction is equal to 0.210. So initially, once we lower the object onto the surface, the wheel is going to slip. It's going to slip against the surface as it rolls. but at some time t, it's going to begin to roll without slipping. So what is the time t? How long does it take before it begins to roll without slipping? And at that time, what is the velocity of the center of mass of the wheel in meters per second? And what is the angular velocity in revolutions per second at that time? So let me show you an animation of this motion in case you're not picturing it. We start off with the wheel rotating. It slips along the surface, but again, at some point, it begins to roll without slipping. So let's see that again. So initially, it's just spinning, no translation, but it picks up that translational motion as it slips against the surface. And then at some point, it's rolling without slipping. So we're basically just asking how long did that take for it to begin to roll without slipping, and how fast is it moving in the translational sense in meters per second, and how fast is it rotating in revolutions per second at that moment. Okay, so let's work this out. Okay, so let's start this problem by drawing a free body diagram of the wheel. So we have a free body diagram of the wheel. And the idea here, of course, is we're going to draw the wheel and then indicate all the different forces that are acting on it. So here's the wheel. The center of mass is marked with an X right there. And the first force that would come to mind would be gravity, or the weight. So W is pointing straight down, and it acts at the center of mass. Now, at the point of contact with the ground right here, there is another force, which is the normal force. So the surface is going to be pushing up on the wheel with a normal force that will indicate as N. Okay, now there's another force, which would be a type of friction, in particular kinetic friction. So the idea is when we first lower the wheel onto the surface, it's going to be sliding relative to the surface. It's going to be rolling with slipping. That means there's going to be kinetic friction between the underside of the wheel and the surface that it's touching. And if we want to understand the direction of that friction, well, we have to take a closer look at how it's rotating. So the wheel is rotating clockwise like this, which means the bottom of the wheel is moving to the left. Okay? So the kinetic friction force should oppose that motion and go to the right. So Fk is acting at that point of contact between the wheel and the ground, and it's going to the right. Okay, another thing that we should do with this diagram is indicate our axes. So the coordinate system we're going to use has the x-axis going to the right, the y-axis going straight up, and the z-axis coming out of the page like this. Okay, so now that we've defined the axes, we can actually also talk about the direction of omega naught. So omega naught, that would be the initial angular velocity of the wheel, and we can get the direction by using the right-hand rule. So if you curl your fingers on your right hand in the direction of that rotation, so you're curling them clockwise, the way the wheel is rotating, you're going to find that your thumb is now pointing into the page. So omega naught is into the page. That's the minus z direction. And we found this by the right-hand rule. Okay, so next we're going to apply Newton's second law, both the translational version of this and the rotational version. Okay, so how about we start by looking at F equals ma, that's the translational version, and we'll focus on the y direction for now. So the net force in the y direction is equal to the mass of the wheel times the acceleration of the wheel. And if we go to the free body diagram, we have two forces that act in the y direction. Those would be the normal force, which points up in the positive y direction. So we have positive n. and then the weight, which is in the negative y direction, so minus W. Okay, what does that equal? Well, there's no motion in the y direction. Okay, all of the motion is in the x direction, left to right. There's no up or down motion, so we have 0 acceleration in the y direction, which means the normal force is simply equal to the weight, which is equal to m times g. Okay, the reason that was important to find out is because the kinetic friction force, Fk, is equal to mu k times n. So again, we're dealing with kinetic friction, not static this time, because the wheel is slipping along the surface, and kinetic friction is given by an equation. We can directly calculate it. Before, when we were dealing with static friction, it's not given by an equation, it's an inequality, so we weren't able to directly calculate it using that inequality, but anyway, now we can. So we have mu k times n, which is mu k times mg, and that's the force of kinetic friction. Okay, so next, let's do F equals ma, Newton's second law for translation in the x direction. So we have the net force in the x direction is equal to m times ax. And from that, if we go to the free body diagram, we'll see there's only one force acting in the x direction, which is kinetic friction acting in the positive x direction, so positive Fk. That equals m times ax. But of course, we just solved for Fk. It's mu k, m times g. That equals m times ax. So canceling out the mass, we get ax is equal to mu k times g. So in other words, we just solved for the linear acceleration of the wheel as it moves along the x-axis. So let's get a number to this. Ax is equal to, okay, the coefficient of kinetic friction, mu k is equal to 0.210, and then g is equal to 9.8 meters per second squared. So here's what we'll get. 2.058 meters per second squared, but keep 3 sig figs on that. And that's our linear acceleration. Okay. So next, let's apply Newton's second law for the rotation of the wheel. And that looks like this. We have the net torque acting on the wheel in the z direction is equal to I times alpha z. And the goal of using this equation is to get the angular acceleration alpha z. Okay, so let's see what we get. When it comes to torque, just want to remind you that torque is given by r cross f, where r is a vector that goes from the axis of rotation to where the force is being applied, and f is just the force. So the weight does not induce a torque. And the reason for that is that r is equal to 0, because that force acts right on the axis of rotation. And in the same way, the normal force does not induce a torque. And the reason for that is if we follow the line of action of the normal force, it goes right through the axis of rotation. So the line of action goes through the axis of rotation. So the only thing that's causing any kind of torque on the wheel is that kinetic friction force. So we only need to worry about that. So when we go back to the equation I just wrote down, the net torque in the z direction is equal to I times alpha z. We're only going to have one term on the right-hand side of the equation. And here's what it will look like. We have r, that's the radius of the wheel, times Fk times sine of 90 degrees, because if we look over here, the r vector would be going again from the axis of rotation down to where the force is applied. And there's a 90-degree angle between that r vector and the kinetic friction force vector. We can also get the direction right by using the right-hand rule. So you take your right hand, point the fingers of your right hand in the direction of r, so point them straight down, then curl them in the direction of Fk, so straight to the right. And you're going to find that your thumb is pointing out of the page, which is the positive z direction. So that torque gets a positive sign. Okay? All right, so on the other side of the equation, we have I, which is the moment of inertia, 1/2 mr squared, and then alpha z. Okay, so the next step we can take is to replace Fk with mu k mg. We worked that out before. That's going to equal 1/2 mr squared times alpha z. Okay, so we can cancel out the mass. We can cancel out one factor of r. And then we can solve for alpha z, which is equal to 2 times mu k times g divided by r. All right, so let's actually put a number to that. We have 2 times the coefficient of kinetic friction, which is 0.210, and then g, which is 9.8 meters per second squared, and then we divide that by r, the radius of the wheel. So that was 12 centimeters, or in meters, 0.120 meters. Okay, so what does this give us? If you crunch the numbers, you're going to get 34.3, positive 34.3 radians per second squared. So this is the angular acceleration of the wheel. Okay, so what can we do with this? Well, we have kinematic equations for the translation of the wheel and for the rotation. So let's write down what some of those kinematic equations are. So kinematic equations. So the linear kinematic equations, the linear motion, also known as the translational motion. Well, we could talk about the velocity of the wheel using this equation, Vx, that's the final velocity along the x-axis, is equal to V naught x plus AXT. Now, in this case, the initial velocity of the wheel is equal to 0 because initially it is not translating. So it's only rotating at the start. So therefore, we can say that V naught x goes to 0, and then Vx, the velocity of our wheel at any given time, is going to be equal to that acceleration we found, AX, which is 2.058 meters per second squared times t. Okay. Now, as far as the rotational motion, or the angular motion, we could say, we have a different kind of kinematic equation, which says omega equals omega naught plus alpha t. But I'm going to put a little z subscript on everything because we're rotating about the z-axis in this problem. So omega z is equal to omega naught z, and then add that to alpha z plus, times t. Yeah. So what can we say about all of these variables? Well, we solved for alpha, and omega naught in the z direction is something we have. Remember, we're rotating at 15 revolutions per second initially, but we'll put a negative sign on that because, as we said earlier up here, omega naught is going into the page in the minus z direction, so it carries a negative sign. And we want to convert this real quick to radians per second. So in every 1 revolution, we have 2 pi radians, which means I can write this as minus 30.0 pi radians per second. So that would be the initial angular velocity of the wheel. So then omega z, this would be a formula for the angular velocity of the wheel at any given time. That would be the initial value, which is minus 30.0 pi radians per second, and then plus alpha, which is 34.3 radians per second squared times t. Okay, so remember, we're interested in when does this wheel start to roll without slipping, okay? So we need to introduce the no slip condition. So when the wheel starts to roll without slipping, we know that the angular velocity, omega, and the linear velocity, VCM, are going to be related just by a factor of r. So we have VCM equals omega times r. But again, we're just talking about the magnitudes here, okay? So we better get the directions right. So the wheel is moving to the right. That would be the positive x direction, which means Vx, the velocity in the x direction, is something positive. On the other hand, the wheel is rotating clockwise, which we showed earlier is the minus z direction. So omega z is something negative, okay? So what we'd say then, using the no slip condition, is that Vx is equal to minus omega times r, omega z times r, I should say, because, again, they have opposite signs. But they're related by a factor of r once the wheel starts to roll without slipping. Okay, so next we're going to make a couple substitutions. For Vx, we're going to make a substitution and put this expression up here that we derived earlier. I'll put a little box around it. And similarly for omega z, we have an expression derived previously, which I'll put a little box around here. And that's what we'll sub in. So for Vx, we have 2.058 meters per second squared multiplied by t. On the right-hand side, we have minus and then omega z, which is negative 30.0 pi radians per second plus 34.3 radians per second squared times t. And then I have to squeeze in the factor of r, so that's 0.120 meters, okay? All right, so what we'll do next is just collect all the factors, all the terms that have a factor of t. So we'll put those all on the left side. So we have 2.058 meters per second squared. And then on the right side, we have minus 34.3 times 0.12, but we're going to add that to both sides, so now it's on the left side, and we have positive 0.120 meters times 34.3 radians per second squared. And again, all of that is multiplying t, okay? Now, on the other side of the equation, I have a term that's just a constant, not multiplying a factor of t, which is we have 30.0 pi radians per second. So we have two negative signs which cancel out, and then that's multiplying 0.120 meters, like this. Okay, so to simplify that, this thing here in the brackets, if you calculate it, comes out to 6.174, and then that's multiplying t. On the other side of the equation, if you calculate 30 pi times 0.12, that comes out to 11.31 seconds. Okay, so now when we solve for t, we get 11.31 seconds divided by 6.174, which gives us 1.832 seconds. So after 1.83 seconds, the wheel is now rolling without slipping. So it has to grind against the surface for 1.83 seconds before it's rolling without slipping. Okay, now to answer the last two questions, how fast is it moving? Well, now that we have the time, we can just plug it right back into that equation for Vx, which is up here. 2.058 meters per second squared times t. So now we have a value of t to plug in. We have 2.058 meters per second squared times t, which is 1.832 seconds. So this works out to 3.770 meters per second, okay? And then omega z, if we want to know how fast it's rotating, we can use this formula. And again, that's minus 30.0 times pi radians per second. And then we're going to add to that 34.3 radians per second squared times time. The time is 1.832 seconds. Okay, so if you calculate that, you're going to get minus 31.41 radians per second. And then just to finish this off, we'll convert that to revolutions per second. So remember, in every one revolution, we have 2 pi radians. So in revolutions per second, this is minus 0.001 revolutions per second. Okay. So at this time, at t equals 1.83 seconds, the wheel is moving to the right. That's the positive x direction. At a rate of 3.77 meters per second. And it's rotating at 5.00 revolutions per second. And again, that would be clockwise. So what happened? As a result of slipping along the surface, the rotation slowed down. But of course, it also picked up some translational motion. And I'm not going to show you this in this problem. You're going to see one like this on the homework, but it lost some rotational motion, it picked up some translational motion, but overall it lost kinetic energy. So it had less kinetic energy at the end of this process compared to the beginning, which makes sense because the whole time it was grinding against the surface, there was kinetic friction acting on it, which should remove mechanical energy. Okay, so that's quite a long problem, but hopefully you see all the different steps and you can apply this to the one on the homework. So that's going to be it for this video. I'll see you in the next one. And actually, that's it for chapter 10. So we finished chapter 10. So I'll see you in the next video. But until then, as always, be safe out there, be healthy, take care.